Studying the deviation of the behavior of real gases from the ideal gas law led us to introduce the discrete nature of gas with the following assumptions. Real gases are composed of a large number of molecules, whether monoatomic or polyatomic, that are in constant random motion. For the sake of simplicity, we will call the gas particles molecules even if they are atoms, as in the case of noble gases. The distance separating the gas molecules is much greater than their size. Although they are not point-like particles and have a finite size and volume, molecules are still small enough to be able to move about fairly freely in space. There also exist repulsive and attractive intermolecular interactions in a real gas that are weak but increasing with the decreasing distance between the molecules. Since the gas particles are separated rather far from each other, they interact only very weakly. Gas molecules in random motion collide with each other and with the walls of the container, and these collisions are considered perfectly elastic. This means that a small fraction of the gas particles is always interacting strongly, that is, colliding. The nature of the collisions is determined by the intermolecular interactions, that is, the repulsive and attractive forces between the colliding partners. The pressure of a gas arises from molecules striking the walls of the container. The assumption on the perfectly elastic nature of the collisions between the molecules is a reasonable one, since we expect no change in the average kinetic energy of the gas molecules constantly colliding with each other and the wall. If the gas in an isolated system where no energy, momentum and mass are transported between the system and its surroundings is in thermodynamic equilibrium, then its state variables like its internal energy do not change in time and it remains in equilibrium. When we present the kinetic theory of gases and the molecular theory of heat, we will discuss in more detail how the discrete nature of gases described here allows us to interpret the macroscopic state variables of a gas, such as its pressure or internal energy, based on the random motion and collision of gas molecules. Now we only give some figures to show how freely gas particles can move in a given spatial volume. In the study of the ideal gas law, we introduce the standard conditions for temperature and pressure by stating that 1 mole ideal gas in such conditions, that is at 0 degrees Celsius and atmospheric pressure, occupies 22.41 liters. Then the amount of species in 1 cubic meter gas at the same pressure and temperature is given by the ratio of 1000 liters to 22.41 liters, which is equal to 44.64 moles. Since the number of particles in 1 mole of substance is given by the Avogadro's number Na, the number of particles in n moles of gas is equal to n times Na, that is 44.64 moles times 6.022 times 10 to 23. Then the number of particles in 1 cubic meter gas is about 2.69 times 10 to 25. If we want to obtain the average volume per molecule in 1 cubic meter, that is the average volume enclosing a single molecule in constant random motion within the spatial volume of 1 cubic meter, then we need to divide 1 cubic meter by the number of molecules in this spatial volume, that is by 2.69 times 10 to 25. This gives 3.72 times 10 to minus 26 cubic meter of average volume per molecule. Now we estimate the linear length associated with the size of this average volume enclosing a single particle by assuming that its cube is equal to the average volume per particle. Then this linear length describing the mean distance between the molecules can be written as 3.72 times 10 to minus 26 cubic meter to the power of 1/3, which is about 3.34 times 10 to minus 9 meters. As a result, the mean distance between the molecules of a gas in standard conditions for temperature and pressure is approximately equal to 33 angstroms. Although this value is derived for an ideal gas, the deviation factor of real gases in standard condition is close to 1, and this distance is still a good approximation in a real situation. There are several methods to determine the molecular diameter for gas species. For example, measuring gas viscosity and apply the kinetic theory of gases provide good estimations for molecular diameters. From such measurements, one can establish that the average molecular diameter for gas species, for example the species in air, is about 3 angstroms. Then we see that the intermolecular distance is about 10 times the size of the molecules in standard conditions. In the case of dilute gases, there are less molecules are enclosed in the same spatial volume, that is, the number of molecules per volume is less and the average intermolecular distance can be much greater than in a gas at atmospheric pressure. As a result, the size of the molecules becomes negligible compared with the intermolecular distance, that is, the gas particles will have more space to move without colliding with one another and the number of collisions will decrease. At the same time, the short-range intermolecular forces become weaker for the ensemble of particles with a greater average intermolecular distance, and these forces become negligible in a dilute gas. In such a situation we have the ideal gas condition, where the ideal gas represents point-like molecules moving freely without any interaction. This means even an ideal gas considered as a continuous substance has a discrete nature, and all its macroscopic properties emerge from the quantities describing the state of the randomly moving and colliding point-like particles in space, as it will be discussed in the kinetic theory of gases. We attributed the deviation of the behavior of real gases from the ideal gas law to the interactions between the gas molecules, that is, to the intermolecular forces acting on the particles of finite size moving randomly in a real gas. When the Dutch physicist Johannes Diederik van der Waals developed his theory on real gases in 1873, he postulated these intermolecular forces, now called van der Waals forces, which are weak electrostatic forces that attract neutral molecules to another in gases, liquids and solids, and are dependent on the distance between the molecules. Van der Waals forces may arise three distinct types of interaction: by orientation, induction or polarization, and dispersion. The interaction by orientation are often referred to as Keesom interaction, after the Dutch physicist Willem Hendrik Keesom, who developed a mathematical description for dipole-dipole interactions. Although such an interaction exists between charges in ionic molecules, Keesom force normally refers to the interaction between the electrically neutral molecules of some species that are permanent electric dipoles. A molecule with permanent electric dipole moment has a distortion in the distribution of electric charge in its structure, and the molecule has a positive and negative end. Because one side of the molecule is always somewhat positive and the opposite side somewhat negative, permanent dipoles have the tendency to align with each other, and this effect results in a net attractive force between them. Keesom interaction includes quadrupole interactions in the molecules whose symmetry is lower than cubic, or in general interactions between permanent multipoles. It is important to note that Keesom interactions are temperature dependent. The second interaction of the van der Waals triad is the interaction by induction or polarization, named after Peter Joseph William Debye, the Dutch physicist and chemist who identified its existence. Debye force is caused by the interaction between permanent dipoles and other molecules, which results in the formation of induced dipoles. Permanent dipoles temporarily distort the electron clouds of other polar or non-polar molecules in their vicinity, inducing their further polarization. Then an additional attractive force arises from the interaction between a permanent dipole with a nearby induced dipole, which is independent of temperature, unlike Keesom interactions. The interaction by dispersion is the third interaction associated with the van der Waals forces, which is also called London dispersion force, since the German physicist Fritz Wolfgang London was the first to recognize this type of interaction between instantaneous or temporary dipoles and molecules. The electrons fluctuating within the electron cloud of a nonpolar molecule have the flexibility to move between electron orbits far away from the nuclei of the molecule and produce a temporary dipole moment. The average of this instantaneous polarization over a short time interval may be zero, and time-varying dipoles cannot align themselves with the actual force of attraction in their vicinity. However, they are able to interact with adjacent molecules and induce properly aligned polarization them, resulting attractive forces. These forces are believed to be the weakest of all van der Waals forces, and the strength of the London dispersion force between two molecules depends entirely on the polarizability of the molecule. Overall, the van der Waals interaction consists of two opposing forces, a long-range attraction and a short-range repulsion. The curve representing the van der Waals potential energy between two interacting molecules is given by the combination of the attractive and repulsive forces. The long-range weak attractive part of the potential is due to the permanent or induced electric dipole moments between molecules, that is, to mutual electrostatic polarization. When the distance between the molecules is greater than 0.6 nanometers, the forces are extremely weak and can be neglected. When the distance between the molecules ranges from 0.6 to 0.4 nanometers, the forces are attractive. They increase slightly as the separation distance between two molecules is reduced until they are so close together that their electron clouds begin to overlap and repel each other electrostatically. This repulsion is therefore due to the size of the molecules and opposes the attractive force as the intermolecular separation decreases. The combined force goes to zero when the interatomic distance reaches approximately 0.2 nanometers, denoted by R0, which is about the length of a typical chemical bond. At closer distances, the combined force becomes very repulsive in nature. When van der Waals developed a discrete model of real gases to describe their behavior by applying the molecular theory of matter, he introduced corrections in the ideal gas equation based on these two characteristics of the electrostatic intermolecular forces in gases. Van der Waals introduced a model for real gases based on the long-range weak attractive and the short-range strong repulsive characteristics of the intermolecular electrostatic forces. These characteristics result in two simple corrections of the picture of ideal gas, that is, the model of point molecules moving independently and colliding with the walls to exert pressure on it. The first correction recognizes the effect of short-range strong repulsive intermolecular forces. We saw that the short-range strong repulsive part of the von der Waals forces has a repulsive core whose radius or naught is of the order of 0.2 nanometers or few angstroms depending on the chemical bond in the molecules. By separating the effects of the repulsive core and the attractive tail, the repulsive core excluding a certain space around a molecule can be interpreted as the spatial volume occupied by the molecule, so other molecules have less room in which to move. Molecules are therefore not point particles but each has a finite volume of its own, which is described by the radius or naught. In this model we can interpret the short-range strong repulsive intermolecular interaction as the result of the interaction between two sphere-shaped molecules with given size and volume described by an effective radius, although the structure of molecules is not necessarily spherical symmetric. If we apply a hard sphere model of the gas molecules with the effective radius or naught or the diameter d, then there will be a distance of closest approach between any pair of particles in the gas. Smaller intermolecular separations are forbidden, as the von der Waals potential suddenly increases to infinity. As a result, the total available volume to the system is less than the total volume of the container enclosing the gas, where the available volume can be expressed as the difference between the volume of the container and the excluded volume that is not accessible to the system. This excluded volume is represented by the spheres of the radius d enclosing the two molecules when they are at closest contact. The volume inside these spheres is not accessible for the center of the neighboring molecule. The excluded volume can be written as the number of molecules N in the system, times a parameter b' describing the excluded volume per particle. Now we determine this excluded volume for the two spheres of effective radius or naught at their minimum separation, where the distance between their centers is the diameter d of the spheres. Then the volume Vp of the particles is given by 4/3 times pi times the cube of their radius or naught, which is equal to 1/6 times pi times the cube of their diameter d. Because the radii of spheres of exclusion are exactly equal to d in the hard sphere model, their volume Ve is given by 4/3 times pi times the cube of d, which is equal to 8 times the volume of the particles. This is the total excluded volume for two molecules in the hard sphere model. Hence, the excluded volume per particle is just half of this value. That is, the parameter b' is equal to 2/3 times pi times the cube of d, or 4 times the volume of the hard spheres modeling the molecules. As already mentioned, the molecules are generally not spherically symmetric and the effective radius or not describing the repulsive core of their von der Waals potential is an approximation applied for the hard sphere model. Another description of the repulsive force between nearby molecules is the soft sphere model, which allows some overlap between the molecules in a close contact, reducing the distance between the centers of the spheres, and in turn the excluded volume per particles for molecules. Because we normally use the amount of species instead of the number of molecules in the system, we introduce the parameter b defined by the product of Avogadro's number Na and the excluded volume per particle b'. Then the excluded volume in the system given by N times b' is equal to N over Na times b. The ratio is simply the amount of species n in the container, and the excluded volume in the system is equal to n times b. Now the available volume for the gas molecules in the container is given by the difference between the volume V of the container and the excluded volume N times b'. As a result, the volume correction for a real gas in a container of volume V is given by the volume V, minus the amount of species n of the gas in the container times the parameter b. The second correction applied for real gases arises from the existence of the long-range weak attractive part of the von der Waals potential. A molecule of a gas in the interior of the container is acted upon by the von der Waals forces in all directions due to the presence of other molecules, which thereby tend to cancel. The pressure of a gas arises from molecules striking the wall of the container, but a molecule approaching the wall experiences a net backward attraction to the neighboring molecules. As a result, a molecule in a real gas hits the wall with less kinetic energy compared with the case of an ideal gas, and the attractive force in turn reduces the effective pressure that the molecule exerts on colliding with the wall. Because each gas particle is attracted to the particles in its neighborhood, we would expect the average energy of the intermolecular attraction to be proportional to the number of interacting pairs of molecules or the density of molecules in the neighbor of any given molecule. This local density can be approximated by the average density ρ bar of the gas, that is the number of molecules N per the volume V of the container. The total energy of attraction for N particles in the system is then proportional to N squared over the volume V. This mutual attraction of the molecules leads to a reduction in volume at the same pressure, acting on the molecules like an additional pressure-like term. As a result, the diminution of the pressure proportional to the number of interacting pairs of molecules at the wall is also proportional to the total energy of attraction for all the molecules per unit volume, that is to A' times the square of the number of the molecules N per the square of the volume V. Here the constant of proportionality A' is a parameter determined by the properties of the real gas. As in the case of the volume correction, we can introduce another parameter A given by the square of the Avogadro constant Na times the parameter A'. Then the product of N squared and A' is given by N squared over Na squared, times A, which is equal to the square of the amount of species N times the parameter A. As a result, the pressure correction of a real gas at the pressure P in the container of volume V is given by the pressure P, minus the square of the number of gas molecules N in the container times the parameter A' over the square of the volume V, or the pressure P, minus the square of the amount of species N in the container times the parameter A over the square of the volume V. These two corrections for volume and pressure are introduced for the state variables of a von der Waals gas to provide a better description of the behavior of real gases. Now we apply these corrections in the ideal gas law for N-mole gas, stating that the pressure P of the gas is equal to the amount of species N times the gas constant R times the absolute temperature T of the gas, over the volume V of the gas. In this formula we replace the volume V with V minus the amount of species N times the parameter B, and the pressure P with P minus the square of the amount of species N times the parameter A, over the square of the volume V. The von der Waals constant A gives the pressure correction of a real gas per the square of the molar density of the gas, and its unit is equal to Pascal times meter raised to the power of 6, over mole squared, or bar times liter to 6 over mole squared. The von der Waals constant B gives the volume correction of a real gas per unit mole, and its unit is cubic meter per mole, or 1000 liters per mole. By applying these corrections in the equation of state of the ideal gas, we can write the pressure P as the amount of species N times the gas constant R times the temperature T over the difference between the volume V and N times B, minus N squared times A over V squared. In the corrected equation of state we express the pressure P of N mole of von der Waals gas as a function of its volume and absolute temperature, where the parameters are the gas constant R, the amount of species N, and the two von der Waals constants A and B. If we use this formula, we can also express the temperature T of the gas or its volume V as a function of the other two state variables and the parameters. The gas constant R is a universal constant, and for a given amount of gas either written in moles or in number of particles we only need to specify the von der Waals constants A and B to describe the equation of state for a von der Waals gas. Because these constants depend on the physical properties of a real gas that is on its molecular structure, we obtain different equations of state for different gas species as opposed to the ideal gas law. If we move the second term from the right-hand side of the equation to the left-hand side and multiply the result by V minus N times B, we obtain the standard form of the von der Waals equation, stating that the sum of the pressure P and the square of the amount of species N times the constant A over the square of the volume V, times the difference between the volume V and N times the constant B, is equal to the gas constant R times the absolute temperature T. In a more convenient form of the von der Waals equation we use the molar volume Vm given by the ratio of the volume V to the amount of species N, and we can state that the sum of P and A over Vm squared, times the difference between Vm and B, is equal to R times T. If we multiply the von der Waals equation by the square of the volume V, we immediately see that it is cubic in the volume of the gas, as opposed to the ideal gas law which is linear in V. Then we expect that the von der Waals equation with its two constants specific to the type of the gas describes the behavior of real gases better than the ideal gas law. However, the von der Waals gas is still an approximation of the equation of state of real gases, which can be seen as follows. The corrected form of the ideal gas law expressed in the terms of the molar volume states that the pressure P is equal to the gas constant R times the temperature T over the difference between the molar volume Vm and the constant B, minus the constant A over Vm squared. Because the first term in the right-hand side can be written as 1 over Vm, times R times T over 1 minus B divided by Vm, P times Vm over R times T is equal to 1 over 1 minus B divided by Vm, minus A over R times T times Vm. Now we do the Taylor expansion of the first term in the right-hand side at 0 by using the formula for the function 1 over 1 minus x with the series 1 plus x squared plus x cubed and so on. Here x denotes B over Vm. And P times Vm over R times T can be written as minus A over R times T times Vm, plus 1, plus B over Vm, plus the square of B over Vm, plus the cube of B over Vm and so on. If we gather the terms with the same power of Vm, then we obtain the following series. 1, plus the difference between B and A over R times T, times 1 over Vm, plus B squared over Vm squared, plus B cubed over Vm cubed, and so on. In the left-hand side we recognize the compressibility factor of the gas, which is expressed by a power series with respect to the reciprocal of its molar volume Vm. We can see the zero-order expansion gives the ideal gas law where the compressibility factor is equal to 1. In the case of the von der Waals gas there are higher-order terms, but only the first-order term has a temperature-dependent coefficient. From the second-order term all the coefficients of the terms are equal to the constant B raised to some power, which indicates that this series is still some kind of approximation of the compressibility of the gas. The general case is given by the virial expansion, where the coefficients of the terms in the expansion depend on the temperature of the gas. These temperature-dependent coefficients called virial coefficients can be calculated for real gases up to an arbitrary order in statistical mechanics. As we have already seen, the equation of state of a von der Waals gas depends on the material properties of the gas, where this dependence is manifested in the von der Waals constants A and B representing the effects of the interactions between the gas molecules on the behavior of the gas. The constant A provides the correction due to the variation in the molecular structure of the particles in the gas, whereas the constant B gives the correction due to the variation in the size of the gas molecules. The table shown here contains the von der Waals constants for several species from simple molecules to more complex ones, demonstrating why these corrections arise from the properties of the molecules of a real gas. For the light elements constituting the gas molecules both the corrections are the smallest, like the atomic gas of helium which has a compact atomic structure and a small size compared to other species in the table. The von der Waals constants of the hydrogen gas are somewhat greater since the structure of a hydrogen molecule is less compact and its size is greater than that of a helium atom. These corrections are gradually increasing with the increasing complexity of the structure and the size of the molecules, as seen in the case of heavier elements like nitrogen and oxygen or the water molecule. For bromine molecules formed by atoms having more than 4 times more electrons than the oxygen atom, the constants A is almost an order of magnitude greater than the same constants for oxygen molecules. The constant B of the volume correction is also almost 2 times greater for bromine than oxygen. In the cases of alkanes like butane, octane and decane the corrections are more than 1 order of magnitude greater than those for the light element. These figures illustrate that real gases constituted of more complex molecules have a relatively high compressibility factor, and the conditions where their behavior can be approximated by the ideal gas law are very limited. In such a situation the von der Waals equation with the proper constants A and B gives much more satisfactory description of the behavior of a real gas. The von der Waals constants can be determined from the experimental data for a given gas. A straightforward method is to measure the pressure, volume and absolute temperature of a given amount of gas and compile a data series of the state variables of the gas. For example, when we determine its compressibility factor by applying the Burnett method, we obtain a chart for the compressibility factor versus pressure for a given temperature and volume. This measurement can be performed at different temperatures by changing the temperature of the thermostat in the Burnett apparatus. As a result, we obtain a data series of the relation between the pressure and the temperature of a real gas confined in a given volume. Then we can use the von der Waals equation to fit the data with respect to the parameters A and B in the equation, and the best fit provides the von der Waals constants for the given gas species. However, there is a more precise method to determine these constants based on the critical temperature, pressure and volume above which gases cannot be liquefied. When we study the isotherms of the von der Waals equation of a given real gas, we will see how its von der Waals constants can be determined from its critical constants. At the same time, the relationship between the critical constants of a real gas and the constants of the von der Waals equation also indicates that the application of the model of the von der Waals gas may turn out to be helpful in the study of phase transitions of matter.